All right, this is the second hour of Physics 1B for October 2nd. And we're going to pick up by looking at an application of what we just talked about, solving this problem called cooling your room. Okay, so it says a typical dorm room or bedroom contains about 2,500 moles of air. We want to find the change in internal energy of this much air when it is cooled from 35 degrees to 26 degrees at a constant pressure of 1 atmosphere. So it starts off with an initial temperature of 35 degrees Celsius, and it goes down to a final temperature of 26 degrees Celsius. And our goal is to find, it says constant pressure of 1 atmosphere, so we'll write down that. And we're given that air has this gamma value that's equal to 1.4. And our goal here is to find the change in internal energy. So that's what we want to find, is what is the change in internal energy, delta U. So from what we discussed just a second ago, we know that if you're talking about a constant volume process, we'll go through the whole process again, I guess. The change in internal energy according to the first law should be equal to quantity of heat that comes in minus the work done by the system. In this particular problem, we're talking about a change in internal energy in a system where probably the volume is constant, because you're talking about a room. The room isn't going to change its size. And since they're giving us some amount of air that we have, we kind of have to assume that that amount of air is not going to change, not significantly, through airflow in or out of the room. So if the volume is constant, then one of these two quantities is zero. Which one of these is zero if the volume is constant? Is it Q or W? It's W, right? The work done by the gas is directly related to the volume change. Directly. It's related to the volume change. And if there's no volume change, that means that delta U is just going to be equal to the heat change, the heat exchange. So this room cools from 35 down to 26. And what I would say is that that heat exchange should then be equal to the number of moles of the gas that we have times the specific heat at constant volume times the change in temperature. Now we're given that gamma is 1.4. It also says that it's air. And if we wanted to go back to the table, at least with what we've been given here, it's slightly off the page, isn't it? Air isn't really one of the ones that's included here. We know that air contains CO2, it contains oxygen, it contains nitrogen. But what value do we use? Well, all we know is that the gamma is 1.4, and we can't just pull CV out of here. Okay, so how do we solve this problem without using CV? So what we can say is that from what we just did a second ago, that the quantity gamma is related to CV because it's equal to CP divided by CV. We also just showed that CP and CV are not, like, they're actually related to each other. CP is equal to CV plus the gas constant. Which means that we should be able to rearrange and solve this for CV in terms of gamma. So let's do that. This would tell us that gamma would be equal to CV over CV is 1 plus R divided by CV. And now we want to isolate CV, so we'll have gamma minus 1 is R over CV, which means that CV is equal to the gas constant divided by gamma minus 1. So we can take that quantity right there, and we could just plug it in right there. So we'll get delta U is N times R over gamma minus 1 times delta T. That's a gamma. Looks like a little R though, doesn't it? And I believe we have all these quantities here, so we can just plug directly in. So delta U is equal to N, number of moles was 2,500. R is 8.31 joules per mole Kelvin. Gamma minus 1 is 1.40 minus 1. And then the change in temperature was 26 minus 35. And again, even though they're in Celsius, the change in temperature is going to be the same in Kelvin, so these units will cancel, and we'll be left with an answer that's just in joules. Because this quantity on the right is negative and everything else is going to give us a positive, our overall answer is going to be negative. Does anyone want to calculate what that is? Okay, so in the chat I'm seeing a few different answers. 467,000, or about 4.67 times 10 to the 5 joules. Anyone have any questions? Does it make sense? Okay. Pretty simple calculation. So, what is next? Next, we are going to talk about the adiabatic ideal gas. An ideal gas in which Q is equal to 0. And this is going to be kind of a... Any questions at all for that? Oops. Pretty straightforward problem. All right, so all I wrote down is adiabatic ideal gas. Adiabatic processes for an ideal gas, that's what I should have written down. That makes more sense. Okay. So, adiabatic process for an ideal gas. Again, adiabatic means that the heat exchange Q with the surroundings is 0. And this could occur as long as this process occurs quickly enough so that there's no time for heat exchange to occur. And again, the example we used was a gas being rapidly compressed by a piston in an internal combustion engine. Really, any system in which you have a gas that's rapidly compressed, that could represent a time when Q is equal to 0. All right. So in such a process, what we know is that the change in internal energy is normally equal to Q minus W, but if this is 0, then what we're going to get is delta U is going to be equal to negative W, but because some of the things that we're going to discuss here require us to do some calculus, we're going to convert that over into just the change in internal energy will be du, and that should be equal to negative dw, which will allow us to use some of the knowledge we have from calculus. All right. All right. The other thing we know specifically for an ideal gas that we used in the last part was that the change in internal energy is really only dependent on temperature, and that we can gain that by looking at this equation right here using the molar specific heat at a constant volume. All right. And then we can equate that by using our other equation for dW. So let's put those together here. So we have on the left-hand side, we'll have N times CV dt. And on the right-hand side, we'll have negative PdV. We're once again going to use the ideal gas law to say that the pressure is equal to N times R times T divided by the volume. So we'll use the ideal gas law so that this will become we have that relationship. I can't forget the negative sign here. We're now going to rearrange things by moving them to the same side. And now what we'd like to do is to get, so in the second term here, there's a dV with the volume. We'd like to get the temperature over here with the dt. And we'll do some other things as well. Specifically, we're just going to isolate dt. So we're going to multiply everything by, let's see, what do we want to multiply by? We want to multiply by 1 over t. And we also want to divide by n, because there's an n in every term. And then we're also going to divide by CV. So we're going to get rid of all the terms in front of the dt here. So multiplying through by that, what we're going to get is, in the first term, just dt divided by t. In the second term, we're going to have the n's will cancel, and the t's will cancel. So we'll have r divided by molar specific heat at a constant volume, and then we'll have a dV over V term. Okay. And I'm just going to say one thing about this here as an aside, as we're doing this derivation here, investigating the adiabatic process for an ideal gas, that because, R over CV. What's R over CV equal to? I think we used that in the last problem, right? Right here. We proved that by going through this process here, we only really need up to this point. So here, I'm going to copy this down so we can have it on the side of this derivation here. I think it's going to paste it right here. Okay, there it goes. Yeah, so we had proved that gamma minus 1 was equal to R over CV. So let's replace that in this too, and then we'll say something about this. So this would then become dt over t plus R over CV is gamma minus 1. So now we've got this nice relationship. It's all equal to 0. So what this tells us is in this adiabatic process for an ideal gas that since, let me write this in a different color. So since gamma minus 1, so gamma was always greater than 1, which means that gamma minus 1 is always going to be greater than 0. It's positive, basically. Gamma minus 1 will always be a positive quantity. That means that the change in temperature and the change in volume have to be opposite of each other for this to be equal to 0. So that means that if the change in temperature, if the change in volume, for example, is greater than 0, that is to say, if it expands, then what does that mean about dt? If the change in volume is positive, we know that volume and temperature are always positive quantities because the temperature here has to be measured in Kelvin. So volume, these are always positive quantities. So if the change in volume is positive, what does that mean about the change in temperature? Temperature has to be negative, yeah? So that's in an expansion process. And then the opposite would be if dV was less than 0, this would be a compression process. In a compression, that means that the change in temperature has to be positive. Okay. Temperature goes up when we compress something. Temperature goes down when it expands. In an adiabatic process. All this is about an adiabatic process. I don't want to confuse you too much, but I do want to point out some things here that I think are some pitfalls that you can avoid. Notice that the equation that we wrote here, which we're gonna turn this into normal math without these dt's and dv's. We'll turn it into just a normal relationship using logs in a second. But notice that we used that, right? But we got a relationship in which the volume can change, right? So just because we used this quantity that has the specific heat at a constant volume, that has this constant, right? It can still tell us something about the way the volume change is related to the temperature change. I mean, it really shows up in this equation here, because if you're talking about constant volume process, then you can't really have a change in volume, right? But just remember that what we're doing is just saying, as long as we know something about a constant volume process, we can relate it to a process in which the volume isn't constant. Okay? We're just using that quantity. And we know that we know that for an ideal gas, that this quantity is equal to du, so we can use it to tell us something about when the volume changes. All right. So we get this equation. We understand to some extent what it means. It really just tells us that when the volume goes up, the temperature has to go down, that this quantity has to be equal to 0. Quantities that are equal to 0 in physics are really useful because if something is changing in such a way that it's always equal to 0, then there's some fixed thing that has to be constant, right? So what we can do then is to integrate both sides of our equation here. On the left-hand side, when we integrate dt over t, we're going to get the natural log of t plus gamma is a constant, so gamma minus 1, and then the natural log of v. What happens when you integrate 0? You get 0, but you also get a constant, right? Like, if I do it's an indefinite integral too at this point, right? So anytime you integrate something, it's always equal to, in this case, the integral of 0 dx, let's say, for example, it wouldn't be equal to x, it would just be equal to 0. But you'd have to add to it a constant, right? Because the derivative of a constant is also equal to 0, right? So I'm just going to say the right-hand side of the equation is just equal to some constant. That constant could be 0, but it doesn't have to be. It's equal to a constant, basically, right? So then we have this relationship, the log of the temperature plus gamma minus 1 times the log of the volume should be equal to some constant. And then what we can do is we can use some log relationships. We can say on the left-hand side, log t, leave it the same. But when I have something multiplied by a log, then I can move that up to the exponent of this thing inside the log. So we can make gamma minus 1 an exponent here for the volume. Say that's equal to a constant. And then on the left-hand side, we can also group together two logs. When you sum two logs, you get the natural log of the product. So you get the natural log of temperature times volume to the gamma minus 1. And that's equal to a constant. But what we could next do then is we could raise both sides to the e power. And the left-hand side would just become T times V times, or volume to the gamma minus 1. That should be equal to e to a constant is, again, just some constant. It's going to turn out that we don't actually care what the constant itself is, although we certainly could figure out what it is. Because now what we want to do is we want to turn this into a relationship kind of similar to something that you do with the ideal gas, which says that if I have the ideal gas law, sorry. If I have something that's equal to a constant, what that means is that if I have two different values of the state variables, so if I know the temperature at one point in time, and I also know the volume at one point in time, and I raise that volume to the gamma minus 1, that this should be equal to the temperature at another state, another point in its state, times the volume also raised to the gamma minus 1. And that relationship works for adiabatic processes with ideal gases. Because we did use the ideal gas law in this derivation, right? Yeah, right here. We used the ideal gas law. So this is only going to work for ideal gases. Okay. It's not exactly a simple relationship, but gamma is just a number, and it tells us that temperature times volume to some exponent is going to be equal to temperature times the volume at another point in its state to that same exponent. And we'll look at examples where we can use this so we can understand better what's being said here. Does anyone have any questions? A lot of math. I think stuff like this usually makes a lot more sense when we apply it, but we're really just coming up with some way to relate a gas as it moves between one state to another state. All right. The next thing we want to do is to use the ideal gas law again. So now we're going to use the fact that that doesn't look good at all. Now we're going to use the fact that according to the ideal gas law, temperature is equal to pressure times volume divided by number of moles times R. So placing that into our equation, I guess we want to use it here. Yeah. So now what we'll have is pressure times volume divided by number of moles times R, and that's multiplied by V to the gamma minus 1, still equal to a constant. And if I have volume times volume to the gamma minus 1, so this is like volume to the first power times volume to the gamma minus 1 power, and if you have two numbers, okay, so this is a relationship, but I should just ask you, what's that equal to? If I have like You guys are answering. I think you know the answer. It's v to the gamma. That's right. And in case you don't remember, the idea is that if you have like x squared multiplied by x to the fifth, then you add the exponents, right? This becomes x to the seventh. So if I take 1 plus gamma minus 1, then 1 minus 1 is, okay. Same base, add powers, exactly. I don't remember, what everybody remembers, but you've probably seen this before. It looks kind of different when you're doing it in just symbols, though, so in case that, this is v to the gamma. So then we would have, let's see, so what we do now is to say that the number of moles is going to be constant, and n is going to be constant. So as long as the number of moles doesn't change, which in this adiabatic process, is that reasonable to say that would always be the case? So let's review. Adiabatic process means that there's no heat exchange with the surroundings. Yeah, if the number of moles of the gas changed, you're actually losing or gaining moles, then I feel like there's no way it could still be adiabatic. There's no way it could still, because if it loses some of its, if some of the gas escapes from your system and gets into the environment, then that's a heat exchange for sure. You'd have to somehow add exactly the same amount of heat that you lost, which the easiest way to do that would be then to just add more moles. So whatever goes out comes in or something like that, which is what happens in a internal combustion engine. But as long as n is constant, then we can multiply the n and the r to the right-hand side and just get that really what we have is p times v to the gamma. This thing is constant now. So we're just going to absorb, not the same constant, we'll call it constant prime or something, but we absorb the n and the r into the constant, basically. And given that relationship, we can do exactly the same thing we did before and say that if p times v to the gamma is a constant for an adiabatic process involving an ideal gas, if I know the pressure at one point in time and I know the volume at another point in time, at the volume at the same point in time, then I can relate that to the pressure and the volume just like that. And we get that expression. Okay, so we get these two expressions here. They both relate, this one relates temperature and volume, this one relates pressure and volume, and we have this gamma quantity that shows up right here. Okay. You don't have any questions about that? Next thing we can do is we can relate these equations that we've gotten here to the work that's done right here. So let's do that. Okay, so if we want to talk about the work done on or by the system, we know that the work done is equal to the negative of the change in internal energy. Wait, did I write that down right? Q is equal to 0. So yeah, work done is equal to the negative of the change in potential energy, or internal energy. But then that internal energy is also equal to this quantity here. So I would say that the work done is going to be equal to the negative of N times CV times the change in temperature. Or writing that in a different way, this would just be negative N times CV multiplied by the kind of final temperature minus the initial temperature. This can be written in another way. This is the way that your book writes it. It multiplies the negative sign inside of here. And it says N times CV times T1 minus T2. This is okay to write it this way as long as you remember that, you know, what these represent. I would say in general, T2 is what I would be calling like the after part or the final temperature. Doesn't have to be the absolute final temperature, just to give the indication that so T1 is going to be your initial temperature. T1. Your book loves to do this. It likes to remove negative signs from equations. It does this a lot in electricity and magnetism, and I think it's kind of confusing. So I prefer the equation that I'm going to box in red here, because then I don't know. But as long as you remember what these things represent, they say the same thing, right? Okay. The other thing we can do is we can relate this back to gamma by using the ideal gas law again. So we can use this again, that the temperature is equal to PV over NR, and we can plug that into this equation here. So what we would get then would be work. Oops. Let's keep using black. We would get that the work done on or by the gas would be equal to, let's see, let's move the N over here. So we're going to replace N times T with PV over R. So we'll get, whoops, PV over R. Delete this one. So then N times T is right here. So we end up getting CV. Both terms are going to have an R in it. T1 is going to be equal to P1V1. T2 is going to be equal to P2V2. And CV over R, we use this relationship again. I think it's gamma minus 1, but now it's inverted. So R over CV is gamma minus 1, which means CV over R is going to be 1 over gamma minus 1. So this is going to be 1 divided by gamma minus 1 multiplied by P1 V1 minus P2 V2. And that should be equal to the work that's done by or on the gas during this adiabatic process. One in which there is no heat exchange with the surroundings. Why don't they just call it like isoheat? Where does adiabatic come from? Where did that name come from? Did anyone know? Like when I read adiabatic, and I haven't like just recently been reading about physics, I don't remember in my brain what it means. I think some of you did though. When I asked the question, some of you very quickly said, when I said, what is adiabatic in the chat, you were very quick to say, oh, there's no heat exchange. So you have some, connection with that. What is the adiabatic? It just feels like such a strange word. Anyway, you have any questions? Again, it's like all these equations. It's hard to internalize these things until you see them kind of used in a process or problem. So your book mentions some things here that I think are important to say. There's some limitations to these equations. Oh, here we go. Late 19th century, from the Greek adiabatos, which means impassable. Okay, so it's like not able to pass is kind of the idea. Doesn't pass through. That makes sense. It'd still be a lot simpler if it was like isoheat or iso. See, it can't be isothermal because that means temperature. I don't know, but yeah. Okay. So your book mentions that we did use the ideal gas law, okay? And the ideal gas law is really only valid for what are called equilibrium states. That is to say, a state in which, the system isn't imbalanced in some way so that it's going to fall in one direction or the other in terms of its pressure, volume, or temperature. So, again, it's really only valid for systems in which there's no heat exchange, and it also, one of the things I said was in order to not have heat exchange, the process has to go really fast. So, in order for this to work, the system has to rapidly change in terms of its volume without departing from equilibrium in some way, which means that it kind of has to go somewhat slowly. So there's a lot of caveats to these relationships we're playing up here. What does that mean? That means that this is an idealized model. It's ideal gas, so it's obviously idealized, but it's approximately true. These relationships are approximately true, is what I'm trying to emphasize here. These are not exact representations of physical processes in nature. They are approximate representations that can give us kind of a guideline, right, for thinking about something. But you shouldn't be surprised if you're working on, like, you go into some engineering field and you're working on improving engines and stuff like that, and you notice that in your engineering courses they're giving you brand new equations and all these kinds of things. The idea is that this is like the physics of it, which means that it's perfect and idealized and dealing with systems that are maybe impossible to realize in nature, but it gives you a guideline for what's going on. It gives you a guideline for what's going on. But you shouldn't take it as the end-all, be-all. These equations are not like Newton's second law. They're not even like conservation of energy. They are approximate examples of what happens to an ideal gas in an adiabatic process. Both of these things are very hard to realize in nature, right? It's very hard to have a system in which there's no heat exchange with your surroundings. And, ideal gases is, again, just a model, right? But for an introductory course in physics, this is a good place to kind of begin to understand these ideas of how work is related to temperature changes, of how work is related to, to pressure and volume changes as well. So let us do this problem. Continuing with the theme of an adiabatic process being a compression in an engine, we're going to look at adiabatic compression in a diesel engine. I'd really like for y'all to actually try to solve one of these problems. It's 11:54. If I gave you 5 minutes, do you think you might be able to try to solve this one? Let's see how that goes. So at 11:59, I'll check in and see how you're doing. We could read it and talk about it real quick too. Compression ratio of a diesel engine is 15:1. That is, air in the cylinder is compressed to 1/15 of its initial volume, as shown in this picture. If the initial pressure is 1 times 10 to the 5 pascals, and the initial temperature is 300 Kelvin, find the final pressure and temperature after adiabatic compression. Part B, how much work does the gas do during the compression if the initial volume of the cylinder is 1 liter? And then we want to use the values CV equal to 20.8 joules per mole Kelvin and gamma equal to 1.4 for air. So we want to find two things here. We want to find final pressure and temperature after compression, and how much work does the gas do during the compression. And I'll just scroll up a little bit, or zoom out a little bit, so maybe you can still see some of these equations here. If I go back down just a little bit, you should be able to see most of these equations. I think you need the other one too. So let me copy this one down. Put it right there. Oops. You don't need both of these though, do you? Maybe you do. We'll see. All right, so I'll give you 5 minutes. Try to solve this problem, and we'll come back and talk about it. Okay, about 1 minute or so more. Is that enough time? Anyone getting close to some answers here? Start with that. Okay, that's been 6 minutes now, I believe. It was 11:56 when I told you to start working after I. So, if you do, you still need time. If you do, what we could do is we could just take a break and then come back and yeah. Does that sound good? That way you'll have plenty of time to finish this. You got an answer for part A. We gotta take a break anyway. So let's just take a break till 12:15. We'll come back. We'll solve this problem, and then we'll move on to. I believe after that we're talking about. Second law. So let's just take a short break until 12:10. And we'll come back and talk about the answers.